Today we are going to discuss about the asymptotic notation, omega notation and theta notation. Omega notation. Omega of g of n is equal to z f of n. There exists a positive constant c and n naught such that 0 less than or equal to c into g of n less than or equal to f of n for all n greater than or equal to n naught. Here two functions are. There are two functions g of n and f of n. So there exists a positive constant c and n naught. Both are positive constant. And here we represent the asymptotic notation as the 0 less than or equal to c into g of n. So c into g of n is equal to or greater than 0 and which is less than f of n for all values of n which is greater than or equal to n naught. So here it is represented by a graph. This is the input value n and here this is the particular value n naught. Then from this, after this n naught, the f of n value will be greater than or equal to c g of n. So we can say that this omega g of n is a set of functions with a larger or some order of the growth of g of n, same growth of g of n. Here c into g of n is less, f of n is greater than or same order of the growth of g of n. So here f of n is a function, not theta. F of n is the set of function with the larger or some same order of the growth of g of n. So g of n is an asymptotic lower bound for f of n. So it is a g of n is lower bound for f of n. ഇവിടെ നമുക്ക് നോക്കിയാൽ തന്നെ അറിയാം ഈ പർട്ടിക്കുലർ വാല്യൂ എൻ്റെ സ്മോളർ വാല്യൂസിന് എൻ നോട്ടിനേക്കാൾ ലെസർ ആയിട്ടുള്ള വാല്യൂസിനെല്ലാം എഫ് ഓഫ് എന്നും ജി ഓഫ് എന്നും ഡിഫറൻ്റ് ആയിരിക്കും. പക്ഷേ എൻ നോട്ട് കഴിഞ്ഞ് ഇതൊരു പർട്ടിക്കുലർ പോസിറ്റീവ് കോൺസ്റ്റൻ്റ് ആണ്. അതിന് ശേഷമുള്ള എല്ലാ വാല്യൂസും നോക്കുവാണെങ്കിൽ എഫ് ഓഫ് എൻ ആയിരിക്കും ഗ്രേറ്റർ വാല്യൂ ഓർ സെയിം ആസ് ദാറ്റ് ഓഫ് സി ഇൻറ്റു ജി ഓഫ് എൻ. അപ്പോൾ ജി ഓഫ് എൻ എന്ന് പറയുന്നത് ലോവർ ബൗണ്ട് ഫോർ എഫ് ഓഫ് എൻ ആണ്. Then omega notation provides asymptotic lower bound and it can be useful when we have lower bound on the time complexity of an algorithm. Generally, the best case performance of an algorithm is not useful. So omega notation is least used notation among all three. And this is an example. Here we are represent 3n plus 2, that is f of n. F of n is equal to 3n plus 2 and omega g of n. So that is g of n is a function that is n. Then നമ്മുടെ condition എന്താണ്? c into g of n is less than or equal to f of n. So c is a constant. Here g of n is a n less than or equal to f of n 3n plus 2. So നമ്മൾ ഇവിടെ constant c, assume that when c is equal to say 3, then it is 3n less than or equal to 3n plus 2 for all values of n. n-ന്റെ വാല്യൂസ് നമ്മൾ നോക്കുവാണ്. n-ന്റെ വാല്യൂസ് എന്ന് പറഞ്ഞാൽ എന്താണ്? n-ന് assume that n naught is equal to 2 കൊടുക്കുകയാണെങ്കിൽ n naught equal to 1 കൊടുത്താൽ എന്താണ് സംഭവിക്കുക? n-ന് 1 കൊടുത്തു കഴിഞ്ഞാൽ 3 into 1 less than or equal to 3 into 1 plus 2. That is 3 less than or equal to 3 into 1, 3 plus 2, 5. So 3 is less than or equal to 5. Correct ആണ്. It is true. If n is equal to 2, 2 ആണെങ്കിൽ 3 into 2 less than or equal to 3 into 2 plus 2. That is 3 into 2, 6 less than or equal to 6 plus 2, 8. So it is also true. So for all values n greater than or equal to 2 എന്ന് കൊടുക്കണമെന്നില്ല, n greater than or equal to 1 ആണെങ്കിൽ also it satisfies. So hence we can say that 3n plus 2 is equal to omega of n. The next example, 5n square is equal to omega of n. Here such that f of n is equal to 5n square, g of n is equal to n, then c into g of n less than or equal to f of n. That is f of n is equal to 5n square. We are assumed that c is equal to 1. C is equal to 1. Then what will be the output? Or c is equal to 5. Assume that c is equal to 5. Then here 5 into g of n is n. n less than or equal to 5n square. 5n always less than or equal to 5n square. Suppose less than or suppose n ന്റെ value n is equal to 1. 1 ആണെങ്കിൽ 5 into 1, 5 less than or equal to n square means 1 square. That is 1. 5 into 1, 5. So 5 is equal to 5 എന്നുള്ള കേസ് വരും. അപ്പോൾ ഇത് ട്രൂ ആണ്. n-ന്റെ 1-ന്റെ കേസിൽ ട്രൂ ആണ്. നെക്സ്റ്റ് കേസ്, if 5 into 5 into 2, n is equal to 2 ആണെങ്കിൽ 5 into 2 less than or equal to 5 into 2 square. So ഇവിടെ 10 less than. നെക്സ്റ്റ് നമ്മൾ എന്നിന് സിക്ക് എന്നിന് 2 എന്നുള്ള വാല്യൂസ് ആണ് അസ്യൂം ചെയ്യുന്നത് ഈ പ്രോബ്ലത്തിൽ. n is equal to 2 എന്ന് പറയുമ്പം ഇവിടെ 5 into c is a constant 5 ആണ് അസ്യൂം ചെയ്തത്. 5 into 2 less than or equal to 5 into 2 square. That is 10 less than or equal to 20. So this condition is true. So നമുക്ക് c എന്നുള്ള വാല്യൂ 5 എന്ന് അസ്യൂം ചെയ്തു. n നോട്ട് എന്ന് പറയുന്നത് 1. സോ ഇവിടെ നമ്മൾ എപ്പോഴും നമ്മൾ ഏതൊരു പ്രോബ്ലം എടുക്കുകയാണെങ്കിൽ നമ്മൾ സിയും അതുപോലെ n നോട്ടും ആണ് ഫൈൻഡ് ചെയ്യുക. ദെൻ ഇവിടെ സി നമുക്ക് 1 ആണെങ്കിലും കണ്ടീഷൻ നമ്മുടെ സാറ്റിസ്ഫൈ ചെയ്യും. സോ സി എന്ന് പറയുന്നത് നമുക്ക് അസ്യൂം ചെയ്യാം. യൂസറിന് ഇഷ്ടമുള്ള ഏത് കോൺസ്റ്റന്റ് വേണമെങ്കിലും അസ്യൂം ചെയ്യാം. ഓക്കെ, നെക്സ്റ്റ് പ്രോബ്ലം ഈസ് if 100n plus 5 is not equal to omega of n square. So our function f of n is equal to 100n plus 5 and g of n is equal to n square. So assume that we need a condition such that omega 0 less than or equal to cn square. Here it is c into n square less than or equal to 100n plus 5. So we will take this f of n 100n plus 5 which is less than. We can rearrange this one as a less than or equal to 100n. We are assumed that 5 is a constant value is changed as a 5n. So total it is 105n. So 105n is always less than 100n plus 5. Then we are here we substitute in the equation cn square less than or equal to 105n. So which is rearranged as Cn square is written as n into Cn. We are taken n is a common outside and Cn minus 105, which is less than or equal to 0. Then n is a positive, so Cn minus 105 less than or equal to 0. And we are implies that from that n less than or equal to 105 by C. But contradiction, n cannot be smaller than a constant and always n is a larger value. So this condition is satisfied. 100n plus 5 is not equal to omega of n square. Then another example, n is equal to omega of 2n. This is true. N cube is equal to omega of n square. This is also true. And n is equal to omega of log n. So n is greater than, that is f of n is greater than or equal to c into g of n. So this is also true. So next notation is theta notation. Theta notation is theta of g of n is equal to f of n. There exists a positive constant c1, c2 and n0 such that 0 less than or equal to, in this function 0 less than or equal to c1 g of n less than or equal to f of n less than or equal to c into g of n for all n values greater than or equal to n0. So here theta of g of n is a set of function at the same growth as, it is not here, theta function is sandwich f of n is sandwiched between c2 g of n and c1 g of n. So c1 and c2 both are constant value and n0 for all values n greater than n0. Here n0 is here n0. Then after that values f of n is sandwiched between c2 g of n and c1 g of n. So theta notation bound functions from above and below. So it defines exact asymptotic behavior. So g of n is in a asymptotically tight bound for f of n. This is an example. 3n plus 2 is equal to theta of g of n. So f of n is equal to 3n plus 2 and g of n is equal to theta of n or n. So we need to find out c1 into g of n is less than or equal to f of n. So here c1, we will assume that c1 is equal to 3 into g of n. G of n is n, which is less than or equal to f of n is 3n plus 2. So 3n is less than or equal to 3n plus 2 for all values n greater than or equal to 1 or n naught is equal to 1. Then this is true. Then next case, second case is f of n less than or equal to c into g of n. So f of n is 3n plus 2 less than or equal to c2 into g of n. G of n is n. So we assume that c2 is equal to 4. So c2 is equal to 4 ആണെങ്കിൽ we assume that c2 is equal to 4. Then 3n plus 5. If for n is equal to 1, assume that n is equal to 1. What is the value? 3 into 1 plus 5, 2, that is 5. 5 is less than or equal to c2 value is 4. 4 into 1, 4. So this condition is false. So n naught value is not 1. So we assume that n is equal to 2. 2 ആണെങ്കിൽ what is here? 3 into 2, 6 plus 2, 8. 8 less than or equal to 4 into 2, that is 8. So this condition is true. N is equal to 2. Then next, n is equal to 3. Here 3 into 3, 9 plus 2, 11. 11 less than or equal to, here it is 3 into 4 into 3, 12. So this condition is also true. So we said that C2 is equal to 4 and N0 is equal to 2. So നമ്മൾ ആദ്യം അസ്യൂം ചെയ്തത് ആദ്യത്തെ കേസിൽ, ഫസ്റ്റ് കേസിൽ ഹിയർ N0 എന്ന് പറയുന്നത് 1 ആണ് അസൈൻ ചെയ്തത്. അതിന് പകരം നമുക്ക് എന്ത് ചെയ്യാം, രണ്ടും കോമൺ ആയിട്ട് എടുക്കാൻ വേണ്ടി N0 ഇവിടെ 2 ആയിട്ട് തന്നെ കൺസിഡർ ചെയ്യാം. സോ ഇവിടെ N0 എന്ന് പറയുന്നത് കോമൺ ആയിട്ട് 2 സെറ്റ് ചെയ്യുക. കാരണം സെക്കൻഡ് ഫംഗ്ഷനിൽ N0 1 എന്നുള്ളത് സാറ്റിസ്ഫൈ ചെയ്യുന്നില്ല. സോ N0 2 ആക്കുക. ദെൻ ഈ കണ്ടീഷൻ സാറ്റിസ്ഫൈ. സോ C1ന്റെ വാല്യൂ എന്ന് പറയുന്നത് 3, C2 is equal to 4 and N0 is equal to 2. For all this condition, this equation will be satisfied. Then next, this is the growth of functions. Here compare, the smallest growth function is log n. The next growth function is n, then n log n, n square, n cube and 2 raised to n. This is the growth of function increasing order. This is the, if n is equal to 10, then log n will be 0.00 microseconds. N value is 0.01 microsecond and n log n it will be 0.033, and for n square it is 0.1 microsecond and n cube is 1 microsecond and 2n it is infinity. So here increasing the n values, these all values will be increased. The next notation is little o notation. Asymptotic upper bound provided by big O notation. It may or may not be asymptotically tight. So for example, here if 2n square is equal to omega of n square is asymptotically tight, but the bound 2n is equal to omega of n square is not asymptotically bound. So we define little o notation to denote the upper bound that is not asymptotically tight. So little o is represented as little o g of n. Here it is represented that little o g of n is equal to set f of n for any positive constant c greater than 0. There exists a constant n naught greater than 0 such that 0 less than or equal to f of n less than c into g of n. In the case of omega g of n, f of n is less than or equal to. Here less equal to case വരുന്നില്ല, only f of n less than case വരുള്ളൂ. So f of n less than c into g of n for all n greater than or equal to n naught values. So this is an example. 2n is equal to little of n square. So here f of n is equal to 2n, g of n is equal to little of o square. So 0 less than f of n less than into c g of n, hold for some constant c is equal to c greater than or equal to 0, but for f of n equal to little of g of n, the bound is f of n less than c into g of n, which hold for all constant c greater than 0. So here our condition is f of n less than, not equal to, less than omega of little of n square. So here f of n is 2n less than n square. So if n is equal to 1, if n is equal to 1, it is 2 less than or equal to n square is 1 square. First condition, for n value it is not satisfied. So n is equal to 2. What is that? 2 into 2, 4 less than 2 square, that is 4. That case also not satisfied. 3 is equal to 2 into n, that is 3 is 6 less than 3 square, that is 9. So this is satisfied. Ni onwards, n is equal to 3 or above വരുന്നതിനെല്ലാം satisfy ചെയ്യും. So for little o is, but 2n square not equal to o n square, because നമ്മൾ ഓൾറെഡി പറഞ്ഞു കഴിഞ്ഞു എന്താണ് എഫ് ഓഫ് എൻ ലെസ് ദാൻ ആണ്, പക്ഷെ ഇവിടെ എൻ സ്ക്വയർ ആണ് രണ്ട് ബോത്ത് സൈഡിലും വരുന്നത്. അപ്പോൾ ലെസ് ദാൻ കണ്ടീഷൻ സാറ്റിസ്ഫൈ ചെയ്യില്ല, ഈക്വൽ ടു കണ്ടീഷനാണ് അവിടെ വരുന്നത് മാക്സിമം. അപ്പോൾ അതുകൊണ്ട് ഇത് സാറ്റിസ്ഫൈ ചെയ്യില്ല. സോ വി ക്യാൻ റെപ്രസെൻറ്റ് as another way, that is limit n of n tends to infinity, f of n by g of n is equal to 0. That is, in little o notation, the function f of n becomes insignificant relative to g of n as n approaches to infinity, or it tends to infinity. If n goes to infinity, then f of n divided by g of n becomes 0. Then next notation is little omega notation. Here little omega notation is represented as like this. Here f of n or little omega g of n is equal to f of n for positive constant c greater than 0, and there exists a n naught value greater than 0 such that 0 less than or equal to c into g of n less than f of n for all n greater than or equal to n naught. Here it is not less than or equal to, only less than cases here. So it is a represents lower bound that is not asymptotically tight. For example, another way we can represent that limit n tends to infinity, when n becomes n approaches infinity, f of n by g of n is equal to infinity. So here example, n square by 2 is equal to omega of n. This will be true, but n square by 2 not equal to w of n square. Then some properties of asymptotic notation. Here one is transitivity. Transitivity is if f of n is equal to theta of g of n and theta of g of n is equal to theta of h of n, then we can say that f of n equal to theta of h of n, that is transitivity. And reflectivity is f of n is equal to theta of f of n, that is reflectivity. And symmetry is if f of n is equal to theta of g of n, if and only if g of n is equal to theta of f of n, that is symmetry. And transpose symmetry is if f of n is equal to big of g of n, if and only if g of n is equal to omega of f of n. These are the some asymptotic properties that is represented here. Then some application of asymptotic notation in algorithm analysis. These notations are important because without expanding the cost of running time the algorithm, we can estimate the complexity of the algorithm. Why asymptotic notation is important? Because they give simple characteristics of an algorithm's efficiency, and they allow the comparison of the performance of various algorithms. So നമ്മൾ asymptotic notation എന്തിനാ യൂസ് ചെയ്യുന്നതെന്ന് വെച്ചാൽ ഏറ്റവും സിമ്പിളായിട്ടുള്ള അൽഗോരിതത്തിൻ്റെ എഫിഷ്യൻസി റെപ്രസെൻ്റ് ചെയ്യാൻ പറ്റും. അതുപോലെ തന്നെ നമുക്ക് ഓരോ അൽഗോരിതത്തിൻ്റെ പെർഫോമൻസ് കമ്പാരിസൺ ചെയ്യാൻ വേണ്ടിയിട്ട് ഈസി ആയിട്ട് പറ്റുന്ന ഏത് നൊട്ടേഷൻ യൂസ് ചെയ്തിട്ടാണ്? അസിംപ്റ്റോട്ടിക് നൊട്ടേഷൻ യൂസ് ചെയ്തിട്ടാണ്. ദാറ്റ്സ് ഓൾ അബൌട്ട് അസിംപ്റ്റോട്ടിക് നൊട്ടേഷൻസ്.